In the classical world of computers, everything boils down to simple logic gates like and not. Well, quantum computing has its own version, quantum gates. But these are so much more than just simple switches. They are these elegant, kind of mind-bending operations that manipulate qubits through superposition and entanglement, and they form the very heart of every single quantum algorithm.
So here's our game plan. We're going to start with the fundamental physics that governs how any quantum state changes. Then we'll dig into the super strict mathematical rules those changes have to follow. From there, we'll build up our practical toolkit of gates, see what they actually look like geometrically, and finally, use them to build one of the most famous and powerful states in all of quantum mechanics.
To really get a handle on quantum gates, we have to start at the very beginning, with the fundamental rule for how a quantum state changes over time. And it all comes down to one of the most famous and, honestly, beautiful equations in all of physics.
And here it is, the Schrödinger equation. This is basically the engine of all quantum dynamics. What it's telling us is that the rate of change of a quantum state is directly tied to the system's total energy, which is all packed into that Hamiltonian operator, h. The key thing here is that this equation describes a perfectly smooth, continuous evolution.
Now here's the crucial insight. If the system's energy stays constant, we can wrap up that entire continuous evolution from the Schrödinger equation into a single, elegant matrix operator, which we call U. This is our time evolution operator. And get this. In quantum computing, this operator is the quantum gate. It's the discrete, controllable step that we use to push our qubit state forward in time.
Okay, so we've got these operators that evolve our system, but they can't just be any old operator. Oh no. They have to obey a critical constraint, a mathematical rule that they absolutely must follow to be physically possible. This is the golden rule of quantum evolution.
Just think about that for a second. A quantum state is defined by its probabilities, right? The probability of measuring one outcome or another has to sum up to 1, 100%, always. So if we apply a gate to change the state, what property must that gate have to make sure the new probabilities also sum up to 1?
The answer is something called unitarity. An operator is unitary if its inverse is its own conjugate transpose. Now, conjugate transpose sounds super intimidating, right? But it's actually just a two-step move. You swap the rows and columns of the matrix, and then you take the complex conjugate of every number inside. And the amazing thing is, for a unitary matrix, this new matrix you just made is exactly its inverse. This property is the mathematical bedrock that guarantees the total length of our state vector, and therefore the total probability, is perfectly preserved no matter what gate we apply.
And this really hits home why this isn't just some mathematical quirk. It is a non-negotiable law of physics. If our quantum gates weren't unitary, the whole theory would just fall apart. Probability could leak out of the system or just appear out of nowhere, and that just can't happen.
A huge and profound consequence of all this is reversibility. Since every single quantum gate U has a perfectly defined inverse, that U dagger we just talked about, we can always undo a quantum operation. This is a massive difference from classical computing. Think about an AND gate. If it spits out a 0, you have no idea what the original inputs were. Information has been permanently destroyed. But in quantum computing, information is always preserved. Everything is reversible, except for measurement, but we'll get to that.
All right, so we've got the physics, we've got the golden rule. Now let's get practical and see how this all translates into the day-to-day language of quantum computing, the powerful framework of linear algebra. How do we actually write this stuff down and make it do work for us?
So a single qubit state, we write it down as a simple two-dimensional column vector. The basis state we call 0 is just the vector 1, 0, and 1 is 0, 1. A general superposition, then, is simply a mix of these two, with these complex numbers, alpha and beta, that hold all the probability information. And look, there is our old friend, that condition at the bottom, making sure the probabilities always sum to 1, just like we talked about.
And this is where it all comes together so beautifully. Applying a quantum gate to a qubit is, mathematically speaking, just matrix vector multiplication. That's it. You take the 2 by 2 unitary matrix for the gate, you multiply it by the 2 by 1 state vector of the qubit, and boom, out pops the new state vector. I mean, think about that. All that complex quantum evolution just boiled down to one clean operation.
Now, the matrix math is awesome and precise, but let's be honest, it's not always easy to picture what's happening. To get a real gut feeling for what these gates are actually doing to our qubit, we need to turn to one of the most elegant visualization tools in all of physics:
This is the Bloch sphere, and it's incredible. Every single possible state of one qubit corresponds to a unique point on the surface of this sphere. The I0 state is sitting right at the North Pole, I1 is down at the South Pole, and all the infinite superposition states are living somewhere on the surface. So what's a quantum gate in this picture? It's simply a rotation of that state vector to a new point on the sphere.
All right, it is time to meet the stars of the show. Let's take a tour of the most common, most fundamental gates you're ever going to see. These are the Lego bricks that you'll use to build pretty much any quantum algorithm you can think of.
First up, the Pauli X gate. This is basically the quantum version of the classical NOT gate. If you look at its matrix, you can see it just swaps the amplitudes for 0 and 1, so it flips the bit. And in our beautiful Bloch sphere picture, this corresponds to a clean 180-degree rotation right around the x-axis. It takes the North Pole straight to the South Pole and vice versa. It's a total flip.
Next, we have the absolute powerhouse of quantum computing, the Hadamard gate. This is, arguably, the most important gate. And why is that? Because it's our #1 tool for creating superposition. It can take a definite state like 0 and just bam, transform it into a perfect 50-50 mix of 0 and 1. Geometrically, it's a 180-degree rotation around this kind of tilted axis, right between the x and z axes. It moves states from the poles to the equator, right into the world of pure superposition.
The S-gate, or phase gate, is a bit more subtle, but don't let that fool you. It's incredibly powerful. It leaves the 0 state completely alone, but it multiplies the 1 state by the imaginary number I. On the Bloch sphere, this is a 90-degree rotation around the z-axis. Now, this doesn't actually change your probability of measuring a 0 or a 1, but what it does change is the qubit's relative phase. And that phase is the secret ingredient that makes quantum interference possible.
So far, we've only been talking about single-qubit gates, but to do anything really cool, we need our qubits to interact with each other. And the CNOT is our go-to, our workhorse, 2-qubit gate. It links the fate of 2 qubits. It does nothing to the second, target qubit, if the first, control, qubit is 0. But if the control is 1, it performs a flip, a NOT gate, on the target. This simple conditional logic, this is how we create entanglement.
Okay, let's put this all together. Let's use our new tools to build something, well, something kind of magical. We're going to combine a couple of our gates to construct one of the most fundamental and famous states in all of quantum information, an entangled Bell state. Here's the recipe, and it's actually surprisingly simple. We start with 2 qubits, both in the plain old 0 state. First, we hit that top qubit with the Hadamard gate, which, as we know, puts it into a perfect superposition. Now here comes the magic. We apply a CNOT gate, using that superposed qubit as the control. The part of the superposition where the control is 1 flips the target qubit, and the result is the Bell state, a perfect superposition of either 0, 0 and 1, 1. The measurement outcomes of these 2 qubits are now perfectly and forever linked, no matter how far apart they are. And the whole time, throughout that entire sequence of operations, from the initial state to the Hadamard to the CNOTs, the unitarity of our gates is our silent guarantee. It ensures this normalization condition always holds true. At every single step, the total probability remains exactly 1. The physics is self-consistent. It just works. So, to wrap this all up, what are the big takeaways? Well, first, quantum evolution is unitary. That means it conserves probability and it's completely reversible. Second, quantum gates are just the physical ways we implement these unitary matrices. Third, we figure out what they do with simple matrix multiplication. Fourth, for 1 qubit, they're just rotations on the Bloch sphere. And finally, gates like the CNOT are what let us weave qubits together to create entanglement, the incredible resource that gives quantum computers all their power.
So I want to leave you with this one last thought. We've spent all this time establishing that the evolution described by quantum gates is smooth, it's deterministic, it's perfectly reversible. And yet, the moment we decide to look at the qubit, the act of measurement, it causes an instantaneous, probabilistic, and totally irreversible collapse of the state. This profound tension between the two sides of quantum mechanics, the reversible evolution and the irreversible measurement, remains one of the deepest, most fascinating, and most fiercely debated puzzles at the very heart of physics.